This is 1 hour of facts about black holes in a soothing voice that studies have scientifically proven to put you to sleep faster because it makes you feel safer and more relaxed. Let's jump into it after you hit like and subscribe so you and others see these videos again. It really helps. Let me know what topic I should put you to sleep with next time. Alright, relax and take a deep breath. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. For a long time, many scientists considered them to be theoretical objects. But in the year 1971, the first physical black hole, Cygnus X1, was discovered. Located about 6,000 light-years away from Earth, this stellar black hole was detected due to its powerful X-rays emitted from the material it consumed, marking a significant milestone in the field of astrophysics. One of the most enigmatic features of black holes is the event horizon, the boundary beyond which nothing can escape the gravitational pull. This radiation occurs because particle-antiparticle pairs form near the event horizon, with one particle falling in and the other escaping, slowly stealing energy from the black hole. Most people think of black holes as being enormous, but there are actually many different sizes. A stellar black hole forms from the remnants of a massive star and may be just a few miles across. In contrast, supermassive black holes, which are found at the center of most galaxies, including our Milky Way, have masses equivalent to millions or even billions of suns. There's even theoretical evidence for primordial black holes, which could be as small as an atom but with the mass of a mountain. These were formed from the high-density regions of the early universe. The first ever photograph of a black hole was captured in 2019 by the Event Horizon Telescope. This black hole exists in the galaxy Messier 87, located over 50 million light-years from Earth. The image vividly displayed a glowing ring of gas and dust surrounding a dark center, the black hole's shadow. Achieving this required coordination between telescopes located all around the world to function as a single Earth-sized observatory. This technological feat exemplified unprecedented global scientific collaboration. Black holes can be detected indirectly by the gravitational influence they exert on nearby objects. In 1994, an essential discovery occurred using the Hubble Space Telescope, which located a supermassive black hole in the center of the galaxy Messier 87. Observations of stars and gas clouds swirling at incredible speeds around an invisible object provided compelling evidence of a black hole with a mass equivalent to 3 billion suns. Such detections proved crucial in our understanding of these cosmic giants. In 2017, scientists made a groundbreaking discovery when they detected gravitational waves from a collision between two neutron stars using the Laser Interferometer Gravitational Wave Observatory, also known as LIGO. While not directly involving black holes, it demonstrated the technology's capacity. Just weeks later, LIGO detected gravitational waves from another type of collision, two merging black holes. This confirmed that black holes can merge, forming a larger black hole and releasing substantial energy in the form of ripples in spacetime. Black holes can spin, a phenomenon that significantly affects their properties. These rotating black holes are the result of the conservation of angular momentum from the original star that collapsed to form the black hole. The spin alters both the geometry of the space around the black hole and the nature of its event horizon. The fastest spinning black holes can rotate at speeds close to the speed of light, leading to complex and challenging to model situations. These rotations can result in the formation and emission of powerful jets of radiation and matter along the black hole's poles. One hypothetical phenomenon associated with black holes is the concept of white holes, which are theoretical opposites of black holes. Whereas black holes capture and compress matter, white holes would hypothetically expel matter. No evidence suggests that white holes exist, but they arise naturally as mathematical solutions within the framework of Einstein's theory of general relativity. Essentially, time-inverted black holes, white holes remain an intriguing area of theoretical physics that spurs much speculation and debate. In a manner not yet fully understood, black holes can contribute to galaxy formation and evolution. Supermassive black holes at the centers of galaxies emit powerful winds and jets that can influence the formation of stars and distribution of gas within the galaxy. These outflows can both trigger and hinder star formation. For instance, the black hole in the center of our Milky Way, known as Sagittarius' star, affects the behavior of nearby gas clouds and star clusters, contributing to the overall dynamics and evolution of the galaxy. The information paradox is one of the most perplexing issues in modern physics relating to black holes. According to classical physics, all information about the matter that falls into a black hole is lost forever, But this contradicts the principles of quantum mechanics, which state that information cannot be destroyed. Stephen Hawking proposed that information might be lost during the process of black hole evaporation via Hawking radiation, but this was debated vigorously. Recent insights suggest that information may be encoded in subtle correlations in the outgoing radiation, though a complete resolution is still awaited. Black holes can accrete matter from their surroundings, forming a structure known as an accretion disk. This disk comprises gas, dust, and other materials swirling around the black hole at immense speeds, heated to incredibly high temperatures, and emitting substantial amounts of radiation, often in the X-ray spectrum. The study of these accretion disks provides vital clues about the environment near black holes and the processes that govern high-energy astrophysical phenomena. Observations of these disks have improved with advancements in telescope technology and computational modeling. In multi-body systems, black holes can cause gravitational slingshots or three-body problem interactions, where a black hole can accelerate another object to high velocities. For example, within dense star clusters, black holes can interact gravitationally with other stars or stellar remnants, sometimes ejecting them from the cluster at high speeds. These high-velocity stars are also known as hypervelocity stars. Studies of such interactions help refine our understanding of gravitational dynamics and the evolution of star clusters and galaxies. The concept of wormholes often comes up in discussions about black holes. Wormholes are hypothetical tunnels connecting two disparate points in space-time, theoretically allowing for faster-than-light travel across vast cosmic distances. While often featured in science fiction, wormholes derive from solutions to Einstein's general relativity equations similar to those describing black holes. Yet there's no empirical evidence for their existence. Scientists ponder whether quantum mechanics or other advanced theories might enable the stability of such exotic space-time bridging constructs. One intriguing aspect of black holes is their potential to encode holographic information, known as the holographic principle. This idea suggests that all the information contained within a volume of space can be represented as encoded data on the boundary of that space. The principle first emerged from studies of black hole entropy and has broader implications for understanding the nature of reality itself. It hints that our three-dimensional universe might be a hologram projected from a two-dimensional surface, an idea being actively explored in theoretical physics. Another lesser-known fact about black holes is the concept of black hole thermodynamics. Bekenstein and Hawking developed the theory stating that black holes have entropy proportional to the area of their event horizon, not volume. This suggests that black holes store information, challenging traditional notions of how thermodynamics applies in a relativistic context. This theory also implies a profound connection between gravity, quantum mechanics, and thermodynamics, hinting at a deeper unified framework that might one day reveal the fundamental workings of the universe. Black holes are not entirely black. They can emit particles and radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, results from particle-antiparticle pairs that form just outside the event horizon. While one particle falls into the black hole, the other escapes, effectively radiating energy away from the black hole. Over colossal timescales, this could lead to the black hole's evaporation, although this radiation is theoretically extremely faint and has yet to be observed. It remains a pivotal concept in our understanding of black hole dynamics. The behavior of light near a black hole is fascinating and counterintuitive. Near the event horizon, the immense gravitational force bends space-time to such an extent that light follows highly curved paths. This can result in the formation of photon spheres, where photons, the particles of light, orbit the black hole multiple times before either escaping or falling in. The strong gravitational lensing effect makes it possible for distant observers to see multiple images of objects behind the black hole, distorted and magnified by its intense gravitational field. Not many know that black holes can create what is known as firewalls. According to some theories, when an object crosses a black hole's event horizon, it might encounter a zone of superheated particles known as a firewall. This idea challenges the classical prediction that an object would experience spaghettification or extreme stretching as it approaches the black hole. The firewall paradox arises from attempts to reconcile general relativity and quantum mechanics, particularly concerning the fate of information falling into a black hole. The debate continues, reflecting the complexities inherent in unifying these fundamental theories. Gamma-ray bursts are some of the most energetic events in the universe and are closely linked to black holes. These bursts occur when massive stars collapse to form black holes, or when neutron stars merge. The resultant black hole formation releases an immense amount of energy in seconds, observable across vast cosmic distances. The connection between gamma-ray bursts and black holes provides critical clues about the birth environments and physical processes of black holes, enhancing our understanding of these high-energy astrophysical phenomena. The study of intermediate mass black holes represents one of the most recent frontiers in astrophysics. Unlike stellar mass and supermassive black holes, intermediate mass black holes, ranging from 100 to 100,000 solar masses, are elusive. While their existence has been hypothesized for years, concrete observational evidence remains sparse. Recently, indirect signatures such as specific types of X-ray emissions and gravitational wave detections suggest these black holes do exist. Understanding them may illuminate gaps in our knowledge about black hole formation and the growth of supermassive black holes. Black holes can interact with one another, sometimes leading to the formation of binary black hole systems. These systems contain two black holes orbiting each other due to their mutual gravitational attraction. Eventually, they may spiral closer and merge, an event detectable via gravitational waves, such as those observed by LIGO. Studying these interactions and mergers helps physicists understand the dynamical behavior of black holes, the emission of gravitational waves, and the influence of these titanic collisions on their surrounding environments. Observing quasi-periodic oscillations in X-ray emissions from the vicinity of black holes has provided another window into their study. These oscillations, detected by space telescopes, are thought to originate from the inner regions of the accretion disks around black holes. They offer clues about the matter dynamics near the event horizon, including the influence of black hole spin and magnetic fields. The patterns and frequencies of these oscillations help astrophysicists develop more precise models of the extreme environments surrounding black holes. Jets emitted by black holes are among the most powerful and collimated outflows in the universe. These relativistic jets can extend for millions of light years, carrying high-energy particles and magnetic fields. The mechanisms behind their formation remain an active area of research, but they are believed to arise from the interaction of the black hole's spin and strong magnetic fields in the accretion disk. Observations of these jets, through radio, optical, and X-ray telescopes, provide invaluable insights into the energetic processes occurring near black holes. The influence of dark matter on black holes is another intriguing and less explored area. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible and detectable only via gravitational effects. Some theories propose that black holes could capture dark matter, leading to unique observational signatures in the behavior of the accretion disk and emitted radiation. Investigating this relationship could shed light on the elusive nature of dark matter and its interactions with ordinary matter. Black hole spin flips are an interesting phenomenon where a black hole's direction of rotation can change. This can occur during mergers with other black holes or massive objects. As angular momentum is exchanged, the black hole's spin axis reorients, affecting the geometry of spacetime around it and the emission of relativistic jets. Observing these spin flips provides vital data about the angular momentum in black hole systems, informing models of black hole growth and the dynamics of galaxy centers. There's an eerie concept known as the no-hair theorem, which states that black holes are entirely characterized by only three externally observable parameters: mass, charge, and angular momentum. This means that any other information about the material that formed a black hole or fell into it is unobservable from outside the event horizon, hence the term no-hair. This theorem simplifies the mathematical modeling of black holes, but also raises questions about the nature and fate of information swallowed by black holes. The evolution of black holes in binary systems can be profoundly complex. When one of the companion stars in a binary system evolves into a black hole, the dynamics of the system alter dramatically. Depending on the distance between the two objects, the black hole's gravity can strip material from its companion, altering its mass and course of evolution. The study of X-ray binaries, where a black hole accretes material from a normal star, helps scientists understand these dynamics and the life cycles of stars and black holes in binary systems. Microlensing is an astronomical phenomenon that occurs when a black hole passes in front of a distant star, bending and magnifying its light due to gravity. This provides a method to detect rogue, isolated black holes that are not part of binary systems and are not actively accreting matter. By observing the magnification patterns, astronomers can infer the presence and properties of black holes that would otherwise be invisible. This technique has led to the detection of isolated black holes within our galaxy, offering insights into their population and distribution. The relationship between black holes and time dilation is another fascinating aspect. As an object approaches a black hole, gravitational time dilation becomes significant. To an outside observer, time appears to slow down for the object nearing the event horizon. If an astronaut were to fall towards a black hole, they would appear to move increasingly slowly to someone watching from afar, eventually seeming to freeze at the event horizon. This time dilation effect stems from general relativity and illustrates the profound influence of gravity on the fabric of space-time. The documentation of tidal disruption events provides another glimpse into black hole behavior. When a star ventures too close to a supermassive black hole, the immense tidal forces can rip it apart in a dramatic event. The remnants of the star then form an accretion disk around the black hole, heating up and emitting intense radiation observable from Earth. These events are rare but offer unique observational opportunities. By studying the light curves and spectral features of tidal disruption events, astronomers gain insights into stellar dynamics and the extreme gravitational environments near black holes. Black holes can also play a role in the formation and evolution of planetary systems. In some cases, planets may form from the material in the accretion disks surrounding black holes. These so-called blanets, short for black hole planets, are hypothetical. But if they exist, they would be subject to extraordinary conditions with intense radiation and gravitational forces. Studying the potential formation and dynamics of such exotic planetary systems can provide unique insights into planet formation in extreme environments. One speculative yet captivating idea is the possibility of Planck star remnants within black holes. These hypothetical objects, proposed by some quantum gravity theories, suggest that at the core of black holes lies a high-density region where quantum effects counteract gravitational collapse. If such remnants exist, they could eventually reduce the black hole to a Planck-sized object over an immense timescale. This notion challenges classic views of black holes and encourages exploration into quantum gravity effects and the ultimate fate of black holes. Black holes exhibit magnetic reconnection events, where magnetic field lines realign and release vast amounts of energy. Such reconnection events have been observed in the jets emitted by black holes and the inner regions of accretion disks. These events can accelerate particles to near-light speeds and produce high-energy radiation. Studying magnetic reconnection in black holes helps astrophysicists understand similar processes occurring in other cosmic environments, such as solar flares and galactic nuclei. Finally, there is the fascinating notion of cosmic censorship, a conjecture proposed by Roger Penrose. It posits that the singularities at the centers of black holes, where the laws of physics break down, are always hidden within event horizons and never exposed to the outside universe. If true, this principle ensures that singularities remain out of reach, preserving the predictability of the universe according to general relativity. However, whether cosmic censorship holds universally remains an open question, driving ongoing theoretical exploration and debate. In 1974, a significant breakthrough occurred when physicist Stephen Hawking proposed that black holes could emit radiation, which we now call Hawking radiation. Prior to this, scientists believed that nothing, not even light, could escape a black hole's immense gravitational pull. Hawking's theory suggested that due to quantum effects near the event horizon, particle-antiparticle pairs are created. One of these particles falls into the black hole, while the other escapes, effectively causing the black hole to lose mass and energy over time. Cygnus X1 is one of the strongest pieces of evidence we have for the existence of stellar mass black holes. Discovered in 1964 as a bright X-ray source in the constellation Cygnus, its nature remained uncertain until the early 70s. The object, now known to be a black hole, is part of a binary system, siphoning material from its companion star. The X-rays we observe come from the heated material just before it crosses the event horizon. The very center of our Milky Way galaxy hosts a supermassive black hole known as Sagittarius, a star. It weighs about 4 million times the mass of our Sun. This enormous gravitational behemoth was inferred by observing the rapid orbits of nearby stars. In 2019, the first direct visual evidence of Sagittarius, a star, was captured through the Event Horizon Telescope, revealing it as a dark region surrounded by brightly glowing accretion material. In 2017, the Event Horizon Telescope project provided the first ever image of a black hole's event horizon. This monumental achievement was focused on the supermassive black hole at the center of the galaxy Messier 87, which is roughly 54 million light-years away. The image revealed a ring of glowing light around a dark central region, giving humanity its first glimpse of a black hole shadow. Black holes are capable of spaghettifying objects due to tidal forces. When an object gets too close to a black hole, the difference in gravitational pull between its nearer side and farther side becomes so extreme that it stretches the object into a long, thin shape. This phenomenon, often referred to as spaghettification, would turn an astronaut into a long, noodle-like strand if they were to fall feet first into a black hole. Black holes possess an event horizon, a point beyond which nothing can escape their gravitational pull. However, it's intriguing to note that from the perspective of an external observer, objects falling into a black hole appear to freeze at the event horizon due to extreme time dilation. Time for the falling object slows down relative to an external observer, making it seem as if it never actually crosses the event horizon. In 1963, mathematician Roy Kerr provided a solution to Einstein's equations that described a rotating black hole, now referred to as a Kerr black hole. Unlike earlier models, Kerr black holes have an ergosphere, a region outside the event horizon where objects cannot remain in place. This rotating black hole's ergosphere can theoretically extract energy, a process known as the Penrose process. Microblack holes, hypothetical tiny black holes, are a subject of considerable interest in theoretical physics. These black holes would be formed at the quantum scale, possibly as a result of high-energy collisions. While the Large Hadron Collider has not yet confirmed their existence, the search continues. If discovered, they could provide insights into both gravitational and quantum realms that remain elusive. Black holes can serve as gravitational lenses, a phenomenon called gravitational lensing. When a black hole passes between Earth and a distant light source, its intense gravity bends the light from that source. This bending can magnify and distort the light, sometimes producing multiple images of the same astronomical object. Gravitational lensing has allowed astronomers to observe objects otherwise hidden behind massive cosmic bodies. In 1939, Albert Einstein and Nathan Rosen theorized about the idea of bridges, now called wormholes, between two different points in spacetime using black holes. These hypothetical structures, sometimes referred to as Einstein-Rosen bridges, suggest the possibility of faster-than-light travel. Although purely theoretical and fraught with paradoxes, wormholes continue to be a fascinating avenue for scientific speculation and exploration. Black holes can merge, creating a single larger black hole in the process. These cataclysmic events are violently energetic, sending ripples through spacetime known as gravitational waves. In 2016, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting these gravitational waves from a black hole merger, confirming a major prediction of Einstein's theory of general relativity. One of the most intriguing aspects of black holes is the concept of entropy in information. Physicist Jacob Bekenstein proposed that the surface area of a black hole's event horizon is a measure of its entropy. This led to a puzzling question: what happens to information that falls into a black hole? The black hole information paradox remains one of the most perplexing issues in modern theoretical physics. Intermediate mass black holes are believed to be the missing link between stellar mass black holes and supermassive black holes. While evidence for these black holes is sparse, some candidate objects have been identified through observations of unusual X-ray sources and gravitational wave detections. Understanding these black holes could provide crucial insights into the formation and growth of supermassive black holes. Black holes may play a crucial role in galaxy formation and evolution. Observations suggest that supermassive black holes are found at the centers of most galaxies, including our own Milky Way. The energy and matter expelled by these black holes through processes like accretion and relativistic jets can influence star formation and the overall structure of the host galaxy. The concept of a Schwarzschild radius, named after physicist Carl Schwarzschild, who first solved Einstein's equations for non-rotating spherical mass, is fundamental to understanding black holes. The Schwarzschild radius defines the size of the event horizon of a black hole. For any given mass, it determines the critical boundary where the escape velocity equals the speed of light. Magnetars, a type of neutron star with extremely powerful magnetic fields, are sometimes considered to be part of the continuum that leads to black hole formation. When a magnetar collapses, its immense magnetic field might influence the characteristics of the resulting black hole. Understanding this transition could offer insights into the boundaries and exotic behaviors of dense cosmic objects. In 1972, physicist Jacob Bekenstein proposed that black holes obey a form of the second law of thermodynamics, suggesting that their entropy is proportional to the surface area of their event horizon. This groundbreaking idea bridged the gap between thermodynamics and gravitational physics, leading to further exploration into the nature of black hole entropy and its role in cosmic events. The discovery of the first binary black hole system, known as LMC-X3 in the Large Magellanic Cloud, opened new horizons in the study of these enigmatic objects. Identified as an X-ray source in 1969, LMC-X3 has provided invaluable insights into the behavior of black holes in binary systems. as well as the mechanisms of accretion and X-ray emission. In 2012, a phenomenon called a tidal disruption event was observed when a star ventured too close to a supermassive black hole and was torn apart. The event, known as Swift J166, was a milestone in astrophysics. It provided direct evidence of the extreme gravitational forces near a black hole and offered new avenues for studying these cosmic monsters. In 2020, astronomers using the Very Large Telescope discovered the closest known black hole to Earth, located just 1,000 light-years away in the system HR 731. While not an immediate threat to our planet, this nearby stellar mass black hole offers an unprecedented opportunity to study the properties and behaviors of such objects within our cosmic backyard. Black holes are thought to play a role in the mysterious phenomenon of dark matter. While there is no direct evidence linking black holes to dark matter, some theories suggest that primordial black holes, formed just after the Big Bang, could account for a portion of the dark matter in the universe. These primordial black holes would be much smaller than those formed from stellar collapse. In 1979, British astronomers discovered an astronomical object known as SS433 harboring a pair of immense jets emanating from a compact object, later identified as a black hole. The jets, moving at a significant fraction of the speed of light, opened new understanding about the outflows produced by accreting black holes and their impact on surrounding environments. Time dilation near a black hole is not just a theoretical concept, but has been indirectly observed. For instance, in 2020, astronomers studying the orbits of stars close to the Milky Way's supermassive black hole, Sagittarius A star, confirmed that time indeed flows more slowly in the intense gravitational field. This finding is one more point of verification for Einstein's theory of general relativity. Pulsars, highly magnetized neutron stars that emit beams of electromagnetic radiation, have been used to indirectly detect black holes. By studying the timing irregularities in pulsar signals, astronomers can infer the presence of a nearby black hole. These observations have provided critical data for understanding the population and distribution of black holes in our galaxy. Observations of the ultraluminous X-ray source M82X1 in the nearby galaxy Messier 82 suggest it might be an intermediate mass black hole. This object exhibits extreme luminosity, far exceeding that of stellar mass black holes, suggesting a mass thousands of times greater than our Sun. Studying M82X1 could help solve the mystery of intermediate mass black holes. Black holes influence their surroundings in many ways, one of which is through the production of relativistic jets. These jets are narrow beams of particles accelerated to nearly the speed of light, often emitted from the regions just outside the event horizon. These energetic jets can span thousands of light years, impacting star formation and distributing heavy elements across galaxies. In 1971, the first candidate for a stellar black hole, Cygnus X1, was affirmed when astronomers observed the binary star system. The system included a massive but invisible object emitting X-rays as it pulled matter from its companion star. This discovery marked one of the first direct pieces of evidence supporting the existence of black holes in our universe. 1994 marked a significant milestone in black hole research with the launch of the Hubble Space Telescope. Its observations revealed that a massive invisible object, a supermassive black hole, resided in the center of the galaxy Messier 87. This finding spurred further research into the prevalence and significance of supermassive black holes in galactic centers. Black holes themselves are invisible, but they can be detected through their interactions with nearby matter. For instance, the material falling into a black hole forms an accretion disk, heating up and emitting X-rays. These X-ray emissions can be detected by telescopes, providing indirect evidence of the black hole's presence and offering data to study its properties and behavior. Gravitational waves are ripples in space-time caused by violent astrophysical events such as black hole mergers, predicted by Einstein's theory of general relativity. The first confirmed detection in 2016 by LIGO came from the merger of two stellar mass black holes. This discovery provided a new way to observe and study black holes, complementing traditional electromagnetic observations. The concept of Hawking radiation suggests that over incredibly long timescales, black holes can evaporate. For a large black hole with a mass similar to our Sun, this process would take a timeframe vastly exceeding the current age of the universe. Smaller black holes would evaporate faster, but the phenomenon remains largely theoretical due to the immense timescales involved. Observations have revealed that supermassive black holes can influence entire galaxies through feedback mechanisms. The energy output from accretion processes in relativistic jets can heat interstellar gas, inhibiting star formation. This feedback loop helps regulate the growth of both the black hole and its host galaxy, playing a crucial role in cosmic evolution. The study of quasars, luminous objects powered by supermassive black holes, has provided profound insights into the early universe. These objects shine brightly as their central black holes accrete mass at high rates. Observations of distant quasars have allowed astronomers to peer back in time, shedding light on the formation and growth of early cosmic structures. In 2018, the discovery of a rogue black hole wandering through interstellar space was reported. This stellar mass black hole, potentially ejected from a binary system, provided a unique opportunity to study black holes not gravitationally bound to any star or galaxy. These rogue black holes are challenging to detect, but may be more common than currently known. Stellar mass black holes formed from the collapse of massive stars usually have masses between 5 and 20 times that of our Sun. However, some mechanisms like the direct collapse of a gas cloud could potentially form black holes without a supernova explosion. Understanding these alternative formation pathways helps refine our models of stellar evolution and black hole demographics. The theoretical concept of firewalls at the event horizon questions traditional views on black hole interiors. Proposed to resolve the black hole information paradox, firewalls suggest a highly energetic zone that would destroy anything falling into the black hole. This idea challenges the notion of a smooth event horizon and remains a hot topic in theoretical physics debates. In 2019, scientists using the European Southern Observatory's Very Large Telescope detected a star orbiting very close to the supermassive black hole at the center of the Milky Way. This star's orbit confirmed the prediction of general relativity known as the Schwarzschild precession, where the closest point in the star's orbit shifts position over time due to space-time curvature. Black holes can spin at exceptionally high speeds, approaching the speed of light. This rapid rotation can cause the space around them to warp drastically due to an effect known as frame dragging. In essence, space and time themselves are twisted in the direction of the black hole's spin. These rotating black holes are called Kerr black holes. Theoretically, they could form distinctive and dramatically different accretion disks compared to non-rotating black holes, making them even more fascinating for scientists to study. A peculiar phenomenon known as spaghettification occurs whenever an object approaches the event horizon of a black hole. In this process, the gravitational gradient between the part of the object closer to the black hole and the part further away becomes extreme. This difference in gravitational pull stretches the object vertically and compresses it horizontally, effectively transforming it into thin strands akin to spaghetti. If you were to witness this, you would see the object lengthen and taper as it approaches the event horizon until it disappears. The Event Horizon Telescope made headlines in 2019 by capturing the first ever image of a black hole located in the galaxy Messier 87. This marked a significant milestone in astronomy and physics, providing visual evidence for objects that were once purely theoretical. The black hole is gargantuan, measuring about 6.5 billion times the mass of our Sun. Its shadow against the bright disk of rotating matter provided a stunning visual representation of the event horizon, confirming decades of predictions. Black holes have a critical boundary known as the Schwarzschild radius, beyond which nothing can escape, including light. Essentially, this radius defines the size of the event horizon. For a black hole with the mass of our Sun, this radius would be about 3 kilometers or roughly 2 miles. If you were to compress any object within its Schwarzschild radius, it would inevitably form a black hole. For Earth, this radius is just under 1 centimeter, meaning the entire planet would need to be compressed to the size of a marble to form a black hole. The Hawking radiation theory proposed by Stephen Hawking in 1974 suggests that black holes can emit radiation. This was revolutionary because it contradicted the earlier belief that nothing could escape from a black hole. Hawking proposed that quantum effects near the event horizon could result in particle-antiparticle pairs being created, with one particle falling into the black hole and the other escaping, effectively leading to a gradual loss of mass and energy from the black hole. Over astronomical timescales, this radiation could theoretically lead to the black hole evaporating completely. Singularities are the core regions of black holes where our current understanding of physics breaks down. In these infinitesimally small points, gravity becomes so strong that neither space nor time can exist in any meaningful sense. The laws of physics as we know them cease to be applicable. What happens within a singularity remains one of the most profound mysteries in modern science. Some theories suggest that new physics, possibly related to quantum gravity, will be required to describe what occurs in these extreme environments. Micro-black holes are hypothetical small black holes that could be as tiny as an atomic nucleus yet possess mass akin to that of Mount Everest. Unlike their massive counterparts, these would have formed in the early universe under high-density conditions. While no micro-black holes have been detected, their existence is a tantalizing idea. Some fringe theories even propose that such black holes could be produced in high-energy particle collisions, like those occurring within the Large Hadron Collider. Although this remains speculative and without empirical evidence, a black hole merger occurs when two black holes come close enough to coalesce into a single, more massive black hole. This event generates gravitational waves, ripples in the fabric of space and time. The first direct detection of these waves happened in 2015 by the LIGO Observatory. These detections have opened an entirely new way of observing the universe, allowing scientists to study black holes and other massive objects in ways that were never before possible. Such mergers often result in enormous bursts of energy, making them some of the most violent events in the cosmos. White holes are the hypothetical opposites of black holes. While black holes trap everything that crosses their event horizon, white holes would theoretically emit matter and energy and would not allow anything to enter. No evidence currently exists to support the presence of white holes in the universe. They remain purely speculative, often featured in discussions about quantum gravity. Some theories posit that a white hole could be the other end of a black hole, essentially serving as an exit point in a different part of the universe or even a different universe altogether. Quasars are incredibly luminous objects powered by supermassive black holes at the centers of distant galaxies. As matter falls into these black holes, it heats up and emits an extraordinary amount of light. These objects are among the brightest in the universe, sometimes outshining their entire host galaxy. Quasars were first identified in the 1960s, and studying them has provided vital insights into the behavior of black holes and the conditions in the early universe. Some quasars are so distant that their light has taken billions of years to reach Earth. The term black hole was first coined by physicist John Archibald Wheeler in 1967. Before that, these objects were referred to as frozen stars or collapsars. Wheeler's terminology made its way into popular science and effectively encapsulated the baffling nature of these entities. The attractiveness of the term helped raise public interest and awareness, leading to an increased focus on black hole research and significant scientific breakthroughs in understanding these enigmatic objects. Black holes can create relativistic jets, which are streams of ionized matter ejected at near light speeds from regions close to the event horizon. These jets can extend for millions of light years, dispersing energy far beyond the host galaxy. The exact mechanisms behind jet formation remain unclear, although magnetic fields are thought to play a critical role. These jets are so powerful that they can affect star formation rates in their host galaxies and even alter the intergalactic medium. Observing these jets provides astronomers with vital information about the black hole's spin and magnetic activity. Gamma-ray bursts, the universe's most energetic explosions, are often linked to black holes. Scientists believe that these bursts can occur during the collapse of a massive star to form a black hole, resulting in a brief but extraordinarily intense emission of gamma rays. Alternatively, they could arise from the merger of two neutron stars or a neutron star and a black hole. Observing gamma-ray bursts has helped scientists understand the conditions that lead to black hole formation and provided crucial insights into extreme physics environments. Cygnus X1 was the first celestial source widely accepted to be a black hole. Discovered in 1964, this X-ray binary system consists of a supergiant star and a compact object. Observations provided convincing evidence that the compact object was indeed a black hole, especially from measurements of gravitational influences on the supergiant star. This discovery represented a critical step in the acceptance of black holes as genuine astrophysical entities, transitioning the concept from theoretical mathematics to observable reality. Black holes play influential roles in galaxy formation and evolution. The energy and jets emitted from supermassive black holes can regulate star formation within their host galaxies. This can either trigger new star formation by compressing gas clouds, or inhibit it by heating and dispersing the gas. The interplay between black holes and their host galaxies is so significant that it's sometimes said, galaxies are forged in the cauldrons of black holes. This relationship challenges previous notions about the isolated nature of galaxies, and introduces the concept of Keoevolution. Intermediate mass black holes fill the gap between stellar mass black holes and supermassive black holes. These black holes are suspected to weigh between 100 and 100,000 times the mass of our Sun. Finding these elusive objects has proven difficult, but several candidates have been identified through their gravitational influence on nearby stars or gas clouds and via X-ray emissions. Confirming their existence is crucial for understanding the processes that lead to the formation of supermassive black holes and the evolution of galaxies. Black holes are not entirely black. They can emit light through a process known as synchrotron radiation. This light occurs when charged particles spiral around magnetic field lines near the black hole, accelerating to near light speeds. The radiation produced in this manner spans many wavelengths, from radio waves to X-rays. Observations of synchrotron radiation have provided invaluable data for understanding the magnetic fields and energetic environments surrounding black holes. This form of radiation is typically seen in the jets emanating from active galactic nuclei and quasars. One of the most counterintuitive aspects of black holes is that they can theoretically contain vast amounts of information. The information paradox, introduced by Stephen Hawking, questions what happens to the information about the state of matter that falls into a black hole. According to quantum mechanics, this information cannot be destroyed. However, classical general relativity suggests that anything crossing the event horizon is lost to the universe. Resolving this paradox is one of the most crucial challenges in modern physics, blending elements of quantum mechanics, thermodynamics, and general relativity. The closest known black hole to Earth is located in the V16 Ophiuchi system, about 3,000 light-years away. Though this might seem distant, it is relatively close in astronomical terms. This black hole is part of a binary system, pulling matter from its companion star and emitting X-rays as a result. The system provides scientists a fascinating laboratory for studying black hole accretion processes and improving our understanding of stellar mass black holes. Discovering and studying nearby black holes like this one helps us refine models of stellar evolution and death. Gravitational lensing is a phenomenon where light from a background object is bent around a massive object like a black hole, creating multiple or distorted images of the background object. This effect, predicted by Einstein's theory of general relativity, has been observed and used to study both the bending object and the source of light. In cases involving black holes, gravitational lensing can provide crucial information about their mass, spin, and surrounding environment. These observations offer windows into the behavior of light under extreme gravitational fields. The Milky Way galaxy hosts a supermassive black hole known as Sagittarius, a star at its center. This black hole is about 4 million times the mass of our Sun. Despite its enormous mass, it is relatively quiet compared to other supermassive black holes, with low levels of accretion and minimal jet activity. Observing Sagittarius A star provides scientists with a unique opportunity to study a supermassive black hole up close. Data collected includes information on how such massive objects interact with their environments and influence their host galaxies. Hawking's area theorem, proposed in 1971, is reminiscent of the second law of thermodynamics. It states that the event horizon area of a black hole can never decrease. This theorem has significant consequences for our understanding of black hole dynamics and thermodynamics. It aligns with the concept that black holes have entropy, a measure of disorder. This relationship between entropy and area suggests that black holes follow similar principles to those governing thermodynamic systems, hinting at deeper connections between gravity, thermodynamics, and quantum mechanics. Primordial black holes are hypothetical black holes that are thought to have formed immediately after the Big Bang. Unlike black holes formed from collapsing stars, these would have arisen from high-density fluctuations in the early universe. They could range in size from subatomic particles to thousands of times the mass of the Sun. If they exist, primordial black holes could account for some portion of dark matter. However, their existence remains unproven, and they are one of the many fascinating but speculative aspects of black hole research. Black holes have been proposed as potential power sources for future civilizations. One concept, the Penrose process, suggests that energy could be extracted from a rotating black hole. This involves sending objects into the black hole's ergosphere, where they would split, with one part falling into the black hole and the other escaping with more energy than it originally had. Another idea involves Hawking energy, capturing the radiation emitted by an evaporating black hole. Both are for now theoretical, but they offer intriguing possibilities for future advanced technologies. The Noether theorem suggests that all black holes, regardless of their initial conditions, can be fully described by just 3 observable parameters: mass, electric charge, and angular momentum. This theorem implies that black holes have no other distinguishing features or hair. While this idea simplifies the study of black holes, it also raises questions about the ultimate fate of information that falls into them. If all other characteristics are lost, this touches upon the information paradox and challenges our understanding of how information is preserved in the universe. Black holes can exert significant influences over vast distances, affecting the orbits of stars and other celestial bodies far from their event horizons. This gravitational influence means that black holes play a crucial role in the dynamical stability of galaxies and star clusters. Even when not actively consuming matter, their gravitational fields can shape the orbits of stars, causing them to follow complex paths. Understanding these gravitational interactions helps astronomers develop accurate models of galactic formation and evolution, showcasing the far-reaching influence of black holes. One of the ways to detect black holes is through the observation of X-ray binaries. In these systems, a black hole accretes material from a companion star, producing intense X-ray emissions. By studying these emissions and monitoring the orbital characteristics of the companion star, scientists can infer the presence of a black hole. The stability and variability of X-ray emissions also provide crucial insights into the accretion disk structure and the processes occurring near the event horizon. These observations have been instrumental in confirming numerous black hole candidates. Black hole thermodynamics explores the relationships between black holes and the laws of thermodynamics. One of the fascinating results from this field is the concept of black hole entropy, proposed by Jacob Bekenstein in the 1970s. Unlike conventional objects, a black hole's entropy is proportional to its event horizon's surface area, not its volume. This realization bridges the gap between thermodynamics, quantum mechanics, and general relativity, offering clues for a future unified theory of physics. It complements Hawking's area theorem, deepening our understanding of the fundamental nature of black holes. The accretion disks of black holes are incredibly hot and luminous, due to the immense gravitational energy converted into heat as matter spirals inward. These disks can reach temperatures of millions of degrees, emitting radiation across the electromagnetic spectrum, from visible light to X-rays. Observations of accretion disks provide insights into the feeding habits of black holes and the physics governing high-energy processes near the event horizon. They are dynamic environments where astonishing gravitational and electromagnetic interactions occur, offering a natural laboratory for studying extreme physics. Black holes can have companions in the form of stars, another black hole, or even a neutron star. These binary systems produce some of the most spectacular astrophysical events. When two black holes merge, gravitational waves are emitted, a phenomenon observed by the LIGO and Virgo collaborations. When a black hole accretes material from a companion star, X-ray emissions are produced. These binary systems are crucial for detecting and studying black holes, as they provide observable electromagnetic signals and gravitational waves, significantly advancing our understanding of compact objects. The concept of black holes dates back to the late 18th century, when Jean Michel and Pierre-Simon Laplace independently proposed the idea of dark stars. These were objects so massive that their escape velocity would exceed the speed of light, making them invisible. Although they lacked a modern understanding of general relativity, their intuitive ideas remarkably anticipated the concept of black holes. Their work laid the groundwork for future studies and illustrates how long the idea of black holes has been part of scientific inquiry, evolving dramatically over the centuries. Black holes can lose mass over time through a theoretical process known as Hawking radiation. This idea, proposed by Stephen Hawking, suggests that black holes emit radiation due to quantum effects near the event horizon. Over incredibly long timescales, this radiation can cause the black hole to evaporate entirely. For massive black holes, this process is exceedingly slow, but for smaller black holes, it could be faster. This process provides a potential mechanism for the eventual disappearance of black holes, connecting the macroscopic world of black holes with microscopic quantum physics. The Planck scale is the realm where quantum gravitational effects become significant, and on this scale, new physics might be needed to describe black holes. At sizes and energies associated with the Planck scale, both general relativity and quantum mechanics break down, requiring a theory of quantum gravity. This scale represents one of the final frontiers of theoretical physics. Studying black holes could provide insights into these elusive quantum gravitational effects, serving as natural laboratories for exploring the limits of our current understanding and potentially leading to groundbreaking discoveries. Black holes are regions in space where the pull of gravity is so strong that not even light can escape from them. These cosmic phenomena warp space-time to such a degree that they create what is known as a gravity well, making the fabric of the universe bend around them. The term black hole was first introduced by physicist John Wheeler in 1967, even though the concept had been theorized much earlier by scientists like Albert Einstein and Carl Schwarzschild. When a star larger than about 25 times the mass of our sun exhausts its nuclear fuel, it can collapse under its own gravity, forming a black hole. This event is known as a supernova, and it results in a cataclysmic explosion that releases an enormous amount of energy. However, The core of the star continues collapsing until it forms a singularity, a point with infinitely small volume and infinite density. The surrounding region is what we call a black hole. Black holes are not actually holes, but rather spheres. The event horizon is the boundary surrounding the black hole, beyond which nothing can escape. Contrary to popular belief, the event horizon is not a physical surface but an imaginary boundary. Once a particle crosses this threshold, it is destined to be pulled into the singularity at the center of the black hole. In a fascinating twist, black holes can actually spin. Just like stars and planets, black holes have angular momentum. When a rotating black hole pulls in matter, it can cause the black hole to gain speed and spin even faster. This rotational energy can significantly alter the geometry of the surrounding spacetime, creating what's known as an ergosphere, an area where objects cannot remain in place and are compelled to move along with spacetime itself. Scientists use the term Hawking radiation to describe the theoretical prediction that black holes can emit radiation. Named after physicist Stephen Hawking, who proposed this groundbreaking idea in 1974, Hawking radiation suggests that black holes aren't completely black. Over incredibly long periods, they can emit particles and lose mass, potentially leading to their eventual evaporation. This surprising revelation challenges the conventional notion that nothing can escape a black hole. Cygnus X1 is a famous stellar mass black hole located in the Milky Way galaxy, about 6,000 light-years from Earth. Discovered in the 1960s through X-ray astronomy, Cygnus X1 is part of a binary system, with a massive supergiant star orbiting it. The discovery of Cygnus X1 provided compelling evidence for the existence of black holes and helped to advance our understanding of their properties. Stellar mass black holes are not the only type of black holes. There are also supermassive black holes, which can have masses ranging from millions to billions of times that of our Sun. These behemoth black holes reside at the centers of most galaxies, including our Milky Way. Sagittarius A star is the supermassive black hole located at the center of our Milky Way galaxy. It has a mass equivalent to about 4 million suns, and it is about 26,000 light-years from Earth. The process of spaghettification occurs when an object gets too close to a black hole, due to the immense gravitational gradient, or difference. Between the side of the object closer to the black hole and the side farther away, the object experiences extreme stretching. This process can stretch it into long, thin shapes, resembling spaghetti. Imagine an astronaut embarking on a perilous journey into a black hole, only to be stretched into strands as fine as pasta as they approach the singularity. Black holes can merge to form even larger black holes. When two black holes spiral close to each other, they generate gravitational waves, ripples in the fabric of spacetime. These waves were first detected directly by the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, in 2015. The observation of these waves confirmed a key prediction of Einstein's general theory of relativity and opened a new window for studying these enigmatic objects. The idea of a wormhole is a hypothetical concept closely related to black holes. A wormhole, or Einstein-Rosen bridge, is a theoretical tunnel that could connect two disparate points in spacetime. While black holes could theoretically be part of this exotic structure, creating a passage through the wormhole would require the presence of exotic matter with negative energy density, something that has not yet been observed. The concept of wormholes remains speculative, but is a staple in science fiction. Despite their formidable reputation, black holes can be surprisingly gentle if they are large enough. If an object were to fall into a supermassive black hole, such as the one at the center of the Milky Way, it would experience much weaker tidal forces compared to a smaller black hole. In theory, a person could cross the event horizon of a supermassive black hole without being immediately torn apart, although they would still be doomed to be pulled into the singularity eventually. Black holes can dance with partner stars in a process known as a binary system. In some binary systems, a black hole and a regular star orbit around a common center of mass. As the black hole pulls material from its companion star, an accretion disk forms around it. The intense gravitational energy released as this material spirals inward causes the accretion disk to heat up and emit X-rays, making these systems detectable by X-ray telescopes. One remarkable discovery in recent years was the first ever image of a black hole, captured by the Event Horizon Telescope collaboration and released in April 2019. The image showed the shadow of the black hole in the center of the galaxy M87, located 53 million light-years from Earth. This historic achievement required the collaboration of more than 200 scientists and a network of radio telescopes around the world, working together to create a virtual telescope the size of Earth. Intermediate mass black holes, with masses between 100 and 100,000 times that of our Sun, are another category of black holes that are more elusive and harder to detect. These black holes are thought to form through the merging of smaller stellar mass black holes and may reside in globular clusters or dwarf galaxies. Finding and studying these intermediate mass black holes can help scientists understand the processes that lead to the formation of supermassive black holes. Black holes can influence their galactic environment through powerful jets and outflows. Some black holes, especially the supermassive ones at the centers of galaxies, can emit jets of charged particles at nearly the speed of light. These jets are launched from the region surrounding the black hole and can extend for thousands of light years into space. The energy carried by these jets can affect star formation and the overall structure of their host galaxy. Microscopic or primordial black holes are a theoretical type of black hole that could have formed in the early universe, shortly after the Big Bang. Unlike stellar mass or supermassive black holes, these primordial black holes could have masses ranging from less than a gram to thousands of solar masses. The existence of primordial black holes remains speculative, but their detection could provide valuable insights into the conditions of the early universe and the nature of dark matter. Black hole information paradox is a long-standing problem that challenges our understanding of physics. When an object falls into a black hole, information about the object's physical state seemingly gets lost to the outside world. However, this contradicts the principles of quantum mechanics, which state that information cannot be destroyed. Resolving this paradox remains one of the biggest unsolved questions in theoretical physics and could lead to a deeper understanding of both black holes and quantum gravity. The idea that black holes could serve as time machines is a fascinating but speculative concept. According to general relativity, the extreme warping of spacetime near a black hole could allow for closed time-like curves, which are paths in spacetime that loop back in time. While the practicalities and paradoxes of time travel render it a topic of science fiction, studying black holes can provide insights into the nature of time itself and the limits of our current physical theories. The concept of a naked singularity is another intriguing but speculative idea in black hole physics. A singularity is the core of a black hole where density and gravity become infinite. In a standard black hole, this singularity is hidden by the event horizon. However, a naked singularity would be exposed to the outside universe, violating the so-called cosmic censorship conjecture. Discovering a naked singularity would challenge existing theories and require new physics to understand. The Schwarzschild radius is a critical concept in black hole physics, first derived by Carl Schwarzschild in 1916. The Schwarzschild radius is the radius of the event horizon for a non-rotating black hole. It is directly proportional to the mass of the black hole, meaning that more massive black holes have larger event horizons. This radius provides a fundamental limit for the size of the event horizon and plays a key role in defining the properties of black holes. In binary systems, where a black hole is paired with a neutron star, fascinating astrophysical phenomena can occur. When the neutron star's energy is drained by the black hole, it can lead to explosive events known as gamma-ray bursts. These bursts are among the most energetic events in the universe, capable of releasing more energy in a few seconds than our Sun will emit over its entire lifetime. The study of such systems offers valuable insights into both black hole and neutron star behaviors. Black holes are not only of interest to astrophysics, but have also captivated the imagination of quantum physicists. The study of black holes has led to the concept of black hole entropy and the formulation of the Bekenstein-Hawking entropy, named after Jacob Bekenstein and Stephen Hawking. This entropy is proportional to the area of the black hole's event horizon and represents the amount of information that could be contained within the black hole. This relationship between entropy and surface area has profound implications for the nature of quantum information. Accretion disks around black holes generate enormous amounts of radiation, making them some of the brightest objects in the universe. As matter spirals into the black hole, it heats up due to friction and releases energy in the form of electromagnetic radiation. This radiation can be so intense that it outshines the entire host galaxy, leading to the phenomenon known as quasars. Quasars are extremely luminous and are powered by supermassive black holes at the centers of distant galaxies. Black holes can also lead to the formation of microquasars, which are smaller versions of quasars found in our galaxy. These systems consist of a stellar mass black hole and a companion star, much like binary systems. The black hole pulls in material from its companion, forming an accretion disk and producing high-energy jets. Microquasars serve as valuable analogs for studying quasars and allow scientists to investigate similar processes on a smaller, more manageable scale. Black holes can impact their surroundings by creating cosmic winds. When matter is drawn into a black hole, not all of it ends up falling past the event horizon. Some material gets ejected by the intense radiation pressure and magnetic fields, creating powerful outflows known as cosmic winds. These winds can sweep through the host galaxy, redistributing gas and dust, and influencing star formation rates. By studying these cosmic winds, astronomers can understand the broader role that black holes play in galactic evolution. Black holes have a profound effect on time itself. According to general relativity, the immense gravitational pull of a black hole causes time to run more slowly near its event horizon compared to farther away. This phenomenon is known as gravitational time dilation. If an observer were to watch an object falling into a black hole, they